Manatees are so cute and cuddly looking. You kind of forget that they're heavier than the car that you drive in. It's pretty sad, but in southern Florida, very large numbers of manatees have been dying due to the toxicity caused by red tide. So this is something that you sometimes hear about even over here on the West Coast. And ultimately, the problem is caused by a single-celled algae, I guess you might refer to that, called Karenia brevis. Maybe algae is not the perfectly correct term. And so let's talk about why this red tide, the organism Karenia brevis, is causing such problems for the manatees. And it really boils down to one molecule or one class of molecules. So Karenia brevis is a dinoflagellate. So it's got this little spinning whip-like tail that propels it. And here's an example of some water that's been just totally overrun by this red tide. And these little dinoflagellates produce a really potent toxin. So quite often the shellfish that are filter feeding in these waters collect this toxin and become super toxic to you. And this is a powerful neurotoxin called brevetoxin that they produce. So if you eat shellfish that have been sitting in those waters, you'll get something called neurotoxic shellfish poisoning. And this molecule is a super duper duper uber potent inhibitor of sodium ion channels, which you need for proper nerve function. You do not want to be ingesting anything with this. And so this is an example of the molecular creativity of this tiny little organism. This little thing here is a better synthetic chemist than any human on the planet Earth. Synthetic chemists have managed to synthesize this from scratch using the kinds of reactions that you learn in Chem 51B and some more advanced stuff, of course, on top of that. And it takes about 123, 130 steps to make a molecule with this kind of level of complexity. But that's well within the bounds of what synthetic organic chemists can do, atom by atom and bond by bond, constructing molecules. Okay, let's get back to our I think Imran, the department tutors put a note over here on this side of the board. I'm not sure if you can see that. There's a review session in, I think, ELH 100 tonight from 5 to 7. Bring your eye clickers. So that's a great service that the department peer tutors are putting on for you. So try to take advantage of that. Okay, so let's get back to let's get back to our order of business here for today. So I said we were going to first cover 5 new reactions. 5 new substitution reactions, all of them electrophilic aromatic substitutions, and that I was going to give you 5 different recipes for making bonds to benzene rings, for substituting hydrogen atoms. Not electronegative leaving groups, but substituting hydrogen atoms on benzene rings with other stuff that's useful. And we already talked about the 3 most useful electrophilic aromatic substitution reactions. I showed you how to put halogens on a benzene ring. I showed you how to put nitro groups on a benzene ring in order, in other words, carbon-nitrogen bonds. I showed you how to make carbon-carbon bonds using the Friedel-Crafts Alkylation reaction. And then just before we left, I showed you this recipe for sulfation, making carbon-sulfur bonds to put sulfonic acid functional groups onto benzene rings. And the 5th reaction that we did not have a chance to get to yet was addition of simple alkyl groups. And I would say that this is the reaction that has the most exceptions that make it so slippery and hard to remember. But let's go ahead and talk about that 5th reaction, Friedel-Crafts Alkylation, as opposed to acylation. Okay, so here's the Friedel-Crafts alkylation. It looks amazingly like Friedel-Crafts acylation. And the only difference is, instead of using this acid chloride type of functional group, we're just using simple alkyl chlorides. You already know how to do substitution reactions on alkyl chlorides. You did that with alkoxides when you did the Williamson ether synthesis. But now I'm showing you that benzene rings can attack. And let me just point out that what's cool that is happening here is that we're replacing that H atom with an isopropyl group in this particular case. So I already mentioned to you once that when you do Friedel-Crafts alkylations, not acylations, but alkylations, you always have to use this benzene starting material in excess. And that makes it intrinsically inefficient. That means at the end of the reaction, 90% of that arene starting material, of your benzene starting material, is not reacted, is just sitting there. So there's an intrinsic inefficiency. It's only efficient with respect to the alkyl chloride. So I just want you to remember that I don't consider this to be efficient with respect to the, I'll write inefficient. It's inefficient with respect to the benzene ring starting material. It's only efficient with respect to the alkyl chloride, where you throw in 1 mole of alkyl chloride, you can get 1 mole of product. But you'll never get all the benzene to react because you always use that in excess. And I expect you to indicate that it's present in excess by writing the word excess if you show me that reaction. Okay, so let's talk about the mechanism for this reaction. It's the same mechanism that we already saw for Friedel-Crafts acylation. So instead of having the chloride attached to a carbonyl, we have the chloride attached to an alkyl group, and we're using the same Lewis acid, aluminum trichloride, powerful Lewis acid that is really desperate for some lone pairs on an electronegative atom like chlorine or oxygen or places like that. So if you put a powerful Lewis acid like aluminum trichloride in this reaction mixture, it will coordinate. The lone pairs on chlorine will attack that in order to make this activated complex. And so what we've really done here is we've turned chloride from a pretty good leaving group into a super duper duper uber leaving group. Wow, that's a super powerful leaving group. Let me draw each of the chlorides on here if I can fit them in. There's a negative charge on, I just attacked aluminum. It was neutral before. Now in this intermediate, it's got a negative charge. That's called an aluminate. An 8 complex when something has a negative charge. And the chlorine, which now has 2 bonds, has to have a positive charge. So let me put that positive charge down here. There it is. And so now this whole thing right here is a great, 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 great leaving group. You can write in great yourself, but that is just a fantastic leaving group. It was okay before, and now it's just amazing. And so that chloride will pop right off. You couldn't stop that chloride now from popping off. And what you generate in your reaction mixture, floating around, very lonely, very desperate, is a carbocation. And so if you have a free carbocation in the presence of a benzene ring, even though benzene ring pi electrons aren't very reactive, it's barely reactive enough. It can do this. It's reactive enough to react with a carbocation. So let me draw that carbocation here now. Here's my, you know, I always like to draw the substituents on my carbocation. It's kind of bugging me that I can't see everything attached. I'll just draw that H there. So it's a secondary carbocation in this case. So now when I have this benzene ring here, we can attack that carbocation. We make a new carbon-carbon bond. And we generate this Arenium ion intermediate. So hopefully you guys have been doing a lot of drawing of Arenium ion intermediates. And I'm going to be super careful to draw the proton on the carbon, because if I don't draw that in, I'm going to forget it, and then I'm going to be in big trouble. So here's my Arenium ion intermediate. And then I've got some sort of a conjugate base floating around. Whoops, let me use my black pen here. Anything can pull that proton off. That proton is so easy to pluck off because this Arenium ion intermediate really wants to get back. Sorry, let me try to use this red pen here. Really wants to get back aromaticity, just like we've shown before. So there we go. We re-aromatize, and now the benzene ring is happy again. It has regained aromaticity. And look at that. I now have an isopropyl group. This is mainly only good for adding secondary or tertiary centers onto benzene rings. And I'll show you, if you want to put a primary carbon with a CH2 group there, we're going to have to do that a different way. And let me explain to you why, in a moment I'll explain to you why that's an issue, why it's only going to be really useful for making secondary or tertiary centers. Now, this new Friedel-Crafts stuff I'm showing you, this aluminum trichloride, that's mighty convenient. You just take any old alkyl chloride, it will work with an alkyl bromide just fine. Aluminum trichloride also works with alkyl bromides, works perfectly well. It actually doesn't matter how you generate the carbocation. If you know other ways to generate carbocations, you can get those to do Friedel-Crafts alkylations as well. So let's take an example of a reaction that that you may know, which is the reaction of double bonds with sulfuric acid. Here I've got two sets of pi bonds. Here's a regular alkene, and here's a benzene ring. Regular alkenes are more nucleophilic. These benzene ring electrons are happy. If I put this alkene in my solution with a powerful acid like sulfuric acid, what will happen is that I'm simply going to protonate that alkene. And that, you've already seen this before when you did hydration of double bonds. So there's my symbol for an acid, HA. And you'll end up protonating that. And it will generate a carbocation. You already knew this stuff from chapter 10. This shouldn't be new to you, the idea that you can protonate a double bond. And it shouldn't be new to you that regular CC double bonds are more reactive than benzene rings. So now that you've got this carbocation, you look at that carbocation, you can't tell whether I generated that with aluminum trichloride or I protonated a double bond. It's going to do the same reaction with a benzene ring. So if I've run this reaction using benzene as my solvent, benzene is a cheap solvent, then this can do that Friedel-Crafts business. So the pi bonds in the aromatic ring can attack that carbocation, and I'm not going to draw the whole mechanism. We don't need to see that Arenium ion intermediate. I'll just draw two arrows to show you that I'm skipping something there. I'm skipping drawing the Arenium ion. Okay, so it doesn't matter how you generate the carbocation. It's just that aluminum trichloride is so new and cool. We try to encourage you to use it in this chapter because you haven't seen that before. Okay, now the bad side of Friedel-Crafts reactions. So the bad side is that, and you already knew this, that carbocations are really wily species. If I tried to do a Friedel-Crafts reaction on this using that aluminum trichloride business, the problem with this is if I use aluminum trichloride to try to pull off this chloride, I'm going to end up with a primary carbocation. And there is no more self-loathing creature than a primary carbocation. Right? It's the second you generate this is trying to figure out ways to rearrange or migrate or do something to get to something that's more stable. And so now it's a race that you just cannot win. It's a race that you cannot win because if there's any group here, like this hydride, that can migrate and give a more stable carbocation, it is going to quickly rearrange. So watch this. If I just move this hydride over like that, it's now a vastly more stable carbocation. And that's faster than this type of a carbocation can react with benzene. So you can't outpace this with an electrophilic aromatic substitution reaction. Before this primary carbocation can react with a benzene ring, it's going to do Friedel-Crafts reactions. Sorry, it's going to do a migration to give a tertiary carbocation, and that will do Friedel-Crafts. So I'm simply going to write FC here, meaning that we do electrophilic aromatic substitution with that T-butyl carbocation. So don't do Friedel-Crafts alkylations with primary alkyl halides. It's always going to rearrange. There's no primary alkyl halide, bromide or whatever, that is not going to rearrange before it adds to a benzene ring. So in other words, even though you started with this primary alkyl halide over here, the product you get is not going to look like that. It's going to be this tertiary thing due to the rearrangement. So that's just one of the problems. So there's all these problems with Friedel-Crafts alkylations. Oh, you have to use excess benzene ring starting material. Oh, alkyl halides rearrange. So just limitation after limitation after limitation. And I believe I'm missing a word here. Friedel-Crafts alkylation without aluminum trichloride. So you don't always have to use aluminum trichloride to generate carbocations. And I think you knew that. I think you knew you could generate carbocations in other ways. Okay, so that's our fifth reaction. You now know 5 powerful recipes for doing electrophilic aromatic substitution reactions. And so now let's take a look at a different issue. Now that you know these 5 powerful recipes for adding substituents to benzene rings, we have to touch upon a really sticky issue here, and that is, well, what happens if there's a substituent already on the benzene ring? What happens if there's something already there? So the problem now becomes, if I've already got one substituent present on my benzene ring, is that there's now non-equivalent positions that I can substitute. Here I'm trying to draw these hydrogen atoms so you can more clearly see. There's 2 sets of protons ortho to methyl. There's two sets of protons that are meta to the methyl group, and there's one proton down at the bottom that's para to the methyl group, and they're not the same. Ortho, para, and meta positions are non-equivalent. There's three different products that you can and will get in this reaction. So if I do a Friedel-Crafts, not a Friedel-Crafts, if I do an electrophilic chlorination, a substitution reaction with this chlorine and FeCl3 recipe, let's take a look at the ratios of these products that we get. So the ortho product, there's two ortho protons. It turns out you get in 42% yield. And then there's one other product that's present in about the same amounts, and that's this para product. It's not exactly the identical yield, but it's pretty close to a 1-to-1 ratio. And that's typical. Whenever you get ortho, you get about the same amount of para. Or whenever you get para, you get about the same amount of ortho. It's not exactly 1-to-1, but close enough. The important thing is that there's almost no meta product in here. In fact, you look at the yield of the meta product, and it's so small that chemists ignore that. Right? Really, this reaction basically just gives you ortho and para product. And so we need to explain that. And I need to give you a set of rules so that you know how to predict, gee, am I going to substitute at the meta position and get high yields of that, or am I going to substitute at the ortho and para positions and get that? And so we're going to spend a lot of time trying to explain to you how to predict this effect. Now, at the bottom of this slide, I'm showing you some basic numbers here for rates and ratios of substitution. And I've got four types of canonical substituted benzene rings. And what I want to do is I want to compare the rates of attack by electrophiles on these ortho, meta, and para positions so that you can see what are the major sites of attack depending on the type of substituent that is attached to the benzene ring. So I'm kind of showing you a summary here, and then we're going to go in and explain why you see these types of numbers. So let me start off over here by trying to basically look at what happens when you have a methoxy group or a hydroxy group or an amino group. The important point is that there's a lone pair on there. That's what distinguishes that. There's a very good, powerful lone pair donor. And that lone pair donor activates by resonance positions like this, the ortho position. I could draw similar resonance arrows to show why there's so much anionic character at the ortho and para positions. And maybe not surprisingly, look how much more reactive the ortho and para positions are. Thousands of times, tens of thousands of times more reactive than the meta position. And there's no resonance structure I can draw that will explain why this meta position should be more reactive. It's less reactive. In fact, it's actually deactivated relative to benzene rings. So all of these numbers are relative to the substitution rate of a simple benzene ring that has no substituents. So the reason why this is less active is because oxygen's electronegative. So alkyl groups accelerate the rates of electrophilic aromatic substitution. So if I put toluene in benzene, toluene has that methyl group on it, it's more reactive than benzene. And not everywhere, just the ortho and the para positions are way more reactive than a simple benzene ring. So if you have an alkyl group, you also favor ortho and para products. Okay, but let's keep going on this list here. What happens if you have a halogen on your benzene ring? Chlorine, or bromine, or less frequently iodine or fluorine. Here, all of the sites substitute more slowly than a benzene ring. It's hard when you've got a halogen on there to get electrophiles to add. Well, it's not that hard. Most of your recipes will work. It's slower than benzene ring. Look, it's almost a tenth as slow or 100 times slower, but all the positions are not equally slowed. It turns out that the ortho and para positions still react faster than the meta position. It's the meta position that really gets slowed here. And finally, when we get to nitro groups, and this will be the same for carbonyl groups or sulfonic acids, now it's different from all of these others that I just showed you. Now it's kind of hard to, because they have so many zeros. The big lesson here is nitro groups really slow down electrophilic aromatic substitution. They really slow it down. But it's not equal at all the positions. They're really slowing down ortho and para positions. And the meta position is, substitution at the meta position is slow, but not quite as much. So as a result, you favor substitution here at the meta position. And you know, I'm not really quite clear. I should have put this in blue. I wish I had this to do over again. I would have drawn these numbers in blue here and these numbers in blue, because the favored sites of substitution or the ortho and para positions. We're looking for the biggest of the three numbers here. So when the nitro group is on there, yeah, so I meant to put the 0.03 and 0.1 in blue, not the 0.001. So here the biggest number, the one that's least deactivated, is that meta position. Okay, so we're going to spend a lot of time explaining these numbers. Some things make it faster to substitute benzene rings, some things make it slower. And they affect the positions of substitution in different ways. So when you start off with a substitution already on the benzene ring and you do electrophilic aromatic substitution, it's going to have an impact. It's going to affect the rate of substitution, and it's going to affect the regiochemistry. So I'm going to start off by, I'll show you this sort of classical analysis of how do you think about the effects? What's the impact of having some kind of a substituent on your benzene ring? And here I'm trying to be very generic by just giving the symbol Y to some sort of a substituent. And then we'll talk in more detail about what Y is. We'll take some cases individually. And the important point is that there's 3 different sites we can attack. There's 2 ortho positions, there's 1 para position, and then there's 2 different meta positions. So here you can see with my arrow pushing, I'm showing what happens if a substituent adds to the ortho position relative to some substituent that's on there. And what you can see is that when you add ortho to some substituent, you generate this Arenium ion where you can see that the carbocation with that empty p orbital that has only 6 electrons, the carbon has only 6 electrons, is right next door to Y. Y is going to have a powerful effect on that carbocation. It's either going to stabilize it a lot or destabilize it a lot. It's going to do something. So there is a very powerful effect. When you substitute ortho, that Y exerts a very powerful effect. And I'll just write strong, I'll write effects, but I mean just effect. So Y is going to have a super powerful effect on ortho substitution. So expect Y to have a big effect there. So now let's take a look at what happens if we add to this metacarbon right here. I'll put a dot so you can see if I pick up these electrons and take them away from the oh, wait, no, I'm doing para substitution. If I attack here at the para position and I take the electrons away from the meta position, and let's scratch this out because I can tell now I made a mistake here. That belongs over here. There we go. If I take the electrons away from this metacarbon and I leave a carbocation there, well, that's not such a good situation. Maybe I can draw a resonance structure to try to somehow move this next to some of the other substituents. And we're going to have to analyze these resonance structures when we draw this Arenium ion to figure out what's the impact of Y when we substitute at that para position. So what I'll do is I'll move down these electrons here and take them away from the carbon that's right next to Y. And when I do that, I can more clearly see that, gee, look at that. In this resonance structure for the Arenium ion, once again, the Y group is right next to that carbocation. When you substitute ortho or para, that Y group ends up right next to the carbocation and the Arenium ion resonance structures. So once again, when you substitute para, there's a very strong effect, very powerful effect of Y on the carbocation. It can really super stabilize it, or it can really super destabilize it, depending on what Y is. And we'll look at that in just a moment. Okay, so ortho and para usually have similar effects. They exert similar effects when you do ortho and para substitution. Y groups exert similar types of effects. But now let's look at the meta position. So it's the same arrow pushing that I had before, right? You can't tell from my arrow pushing where I'm substituting. In this case, I'm lifting up the electrons. I'm substituting at the meta position, and I'm lifting the electrons away from the para carbon. And so that leaves the positive charge down here at the para position. And I can't see any effect of Y on that, but maybe if I draw some kind of a resonance structure, maybe Y will end up right next to my carbocation again. So let's take these electrons and swing them over. That'll make that carbocation happy. And so now when I draw this Arenium ion resonance structure. So I hope you've been working lots of problems in Chapter 18 in the Gorzinski-Smith textbook, because it will have lots and lots of chances for you to practice drawing Arenium ion resonance structures. And this is the kind of question that they love to ask you about on standardized exams to professional schools like the MCAT and the DAT. Okay, that's still not happy. That looks like just a secondary carbocation. Maybe there's another resonance. Maybe if I keep drawing resonance structures, I'll get to some resonance structure where there's some way for Y to have an influence there. So let me move that by resonance. Let me satisfy that carbocation one more time. So here's one more Arenium ion resonance structure. And here's my substituent at the meta position. And, you know, that's it. I don't have any more resonance structures I can draw. None of these resonance structures for meta substitution put the Y group right next to that carbocation. So the bottom line is that when you substitute ortho and para, Y is either going to make that carbocation great, or it's going to make that carbocation really suck. And when you put substituents in electrophilic aromatic substitution at the meta position, you know, the Y is kind of far away from those carbocations. It's not going to have a strong effect. It may have a weak effect, but it's not going to have a super duper strong effect like it will at the ortho and para positions. So now, let's take a look at what happens when we put real groups in place of Y instead of this fictional sort of Y symbol. Let's analyze some patterns of electrophilic aromatic substitution so that we can see how either if Y is a donor, how's that going to affect the Arenium ion, or if Y is some kind of positively charged substituent, how that might make the carbocation very uncomfortable. Okay, so what I'm going to do here is I'm going to try to imagine the effects of these various types of functional groups. And what I'm going to do is I'm going to draw a real atom in place of Y for those Arenium ion resonance structures. But I'm not going to draw all three of them, just because it takes too much time. We don't have enough time in lecture to draw all three of those different types of Arenium ions. I'm only going to draw the ortho substituted Arenium ion resonance structure. So when you substitute ortho to an atom that has a lone pair on there, for example, nitrogen, doesn't matter whether R is a hydrogen atom or an alkyl group there. So if you add ortho to an amino group, or a dialkyl amino group, just imagine how great it is to have a lone pair right next door. That lone pair can donate right into that, and it does, can donate right into that, to that carbocation and stabilize it. It will satisfy the octet rule. So resonance, if you've got a nitrogen lone pair on your substituent, resonance will really stabilize the addition at the ortho position, because that Arenium ion gets super stabilized by the lone pair. I can't resist here. I have to draw this para substituted Arenium ion. So just to prove to ourselves that it's the same idea. If you substitute at the para position when there's an amino group on the benzene ring, you end up with, you can draw a resonance structure that looks like this, in which, once again, the lone pair is right next door to that empty carbocation, and once again, that lone pair can super stabilize. You can either make your arrow, your curved arrow end to show you're making a double bond, or make it attack the positive charge as long as you're precise. Bottom line is the lone pair donates into that carbocation so it doesn't have just 6 electrons. So any one of these substituents that has a lone pair will have that same effect. It will help to favor substitution at the ortho and para positions, because those lone pairs will be able to donate in to the empty p orbital in one of those Arenium ion resonance structures. So ortho and para, all of these substituents that have lone pairs favor substitution at the ortho and para positions because they stabilize the Arenium ions. You're going to find that there's a very similar effect when you have an alkyl group on your benzene ring. And so let's redraw these Arenium ion resonance structures so we can see why it's so good to add ortho and para when you have an alkyl group. And it really doesn't matter what the alkyl group is. I'll make it an ethyl group. So here are my Arenium ions. Here's one of the important Arenium ion resonance structures when I add to the ortho position. So when I add ortho, maybe I should label that ortho. And maybe I should label that this is para substitution. And here, if I add to the ortho substitution of an alkyl benzene, look at that Arenium ion. That's like a tertiary carbocation instead of secondary. And you know that tertiary carbocations are better than secondary carbocations. That alkyl group will lead to a more stable carbocation. And likewise, if I add to the para position of an alkyl substituted benzene ring, I'll end up with an Arenium ion in which one of the Arenium ion resonance structures is a tertiary carbocation. So if you have alkyl groups on benzene rings, yeah, there's no lone pairs on an alkyl group, but you already knew that alkyl groups can stabilize carbocations. Not as much as a lone pair, but any kind of an alkyl group, you know, ethyl, isopropyl, T-butyl, that just has C's and H's there will lead to ortho and para substitution. Okay, so these are the kinds of substituents that favor ortho and para substitution. And since I'm making a big deal about that, maybe it should be obvious that you don't always favor ortho and para substitution. As I mentioned with that nitro group, there are some things that will favor meta substitution. And let's take a look at what types of substituents will favor meta substitution. So what I'm going to do is I'm not going to draw the rhenium ion resonance structure for the meta substitution product, ironically. I'm going to once again draw for these types of substituents. And notice what's particular about these. Plus charge, there's a partial positive charge on this sulfur because oxygens are electron withdrawing. Let's go ahead and start off by drawing a tetraalkyl ammonium where I have 3 methyl groups on this, and they could be 3 protons as well. But when I draw the Arenium, if I draw the Arenium ion resonance structure that would result from attack ortho to that substituent, let's take a look at what that's going to look like. I hope you can tell that sucks. That just sucks. Right? If you're an electron-deficient carbocation, the last thing in the world you want is to have some sort of cation right next door to you. That's the worst situation on the planet Earth. So what you'll find is it's very similar whether you substitute ortho or para. If you have some sort of cationic type of substituent or electron-deficient substituent, you do not want to substitute ortho and para. You'll end up in this situation where that positively charged or cationic group is totally screwing over that Arenium intermediate. So meta substitution is kind of the default here. It's because all of these substituents screw over ortho and para substitution so badly that you only get meta substitution. So it's not that they make meta better, it's just that they don't make it as bad as they make the ortho and para. So they really mess up the ortho and para substitution so badly that you get meta substitution as the default there in those cases. Now, I want to draw these, at least one of these possible carbonyl derivatives. This last group here can be either a ketone where there's a methyl. It can be an aldehyde where I have an H attached here. It can be an ester where there's an OR group attached to the carbonyl. But let's start off just by drawing out this Arenium ion resonance structure where I have a ketone, just so I can be more clear about the effect of having a ketone at that position. And I'm only going to draw one of the possibilities, this ortho substituted Arenium ion resonance structure. So when you add to the ortho position of a benzene ring that has a carbonyl group attached to it, we have to remember that there's another resonance structure for carbonyls that we need to think about. Oxygen is electronegative. And when we draw this other resonance structure and make oxygen happy by giving oxygen the electrons, now we can see why this is so bad. The true effect of a carbonyl group substituent is that a carbonyl is kind of like a carbocation. When you get to Chem 51C, you're going to do a million reactions where you add nucleophiles to carbonyl groups. In the Chem 51LB labs, you added a hydride to a ketone group. And all of that is because the carbonyl carbon has a substantial partial positive charge. So once again, this is awful. That's awful. So if you have esters, ketones, or aldehydes on a benzene ring, they really mess up substitution at the ortho and para position. And it's the same for a nitrile kind of group there. Okay, so substituents have a powerful effect on the ortho and the para positions. They have a really powerful effect. They either help substitution at the ortho position, like things that add lone pairs, or they really mess up substitution at the ortho and para positions, and by default leave you with meta-substitution as the preferred reaction pathway. And so I expect you to be able to draw Arenium ion resonance structures, or at least compare them so that you can say, gee, does that substituent that was already there have a good effect or a bad effect on the Arenium ions? That's kind of standard stuff when you look at standardized exams, like the MCAT or the PCAT or the OAT, all those types of exams, the graduate record exam, the GRE in chemistry, if you go to graduate school. Okay, so, you know, when you put a substituent directly next to a carbocation, there's two completely different effects that we need to think about. Oxygen has two completely different types of effects on neighboring carbocations, and I want to dissect out those two effects and treat them individually because they're not the same. And effect number one, let me enumerate these. Effect number one out of these two effects has to do with the fact that oxygen is electronegative. There are lots of protons in the nucleus of oxygen. There's more protons in the nucleus of oxygen than there are in a carbon nucleus. And that's why oxygen is so electronegative. It's those protons in the nucleus of oxygen. So if I put an electronegative atom, oxygen, nitrogen, chlorine, fluorine, next to a carbocation, you'll end up with this effect of electronegativity. It's sometimes that's called an inductive effect. Some books call that inductive effect. Some books call that a polar effect because they're afraid to use this word inductive effects. You know, the bottom line is it's just electronegativity. So I hope you can see that, gee, if I've got an electronegative atom here, that's not such a good thing to have there. But there's a completely different effect on top that you have to add to or subtract from that competes sometimes with this destabilization. So actually, let me just, to make this clear, let me draw an Arenium ion that has an oxygen substituent at that position, like we've already done before. So when you have an oxygen substituent on your Arenium ion intermediate, this effect of that electronegative atom is to destabilize. So it's destabilizing that carbocation. In fact, that oxygen, the electronegative effect, destabilizes carbocations at all the positions. Ortho, right here at this position, ortho, meta, para. But the strongest effect is when it's close by. Closer you are, the stronger that electronegative effect is. And if you wanted to estimate that, I'm sure you could break out Coulomb's law and say charge times charge divided by distance and come up with some number. It's distance dependent. Okay, now let's take a look at this other effect, and that is resonance donation. This is a completely different effect from that electronegativity effect. Lone pairs, doesn't matter what the lone pair is attached to, can donate into carbocations. Look, here's the resonance structure. So you should already know that you can have resonance stabilization of carbocations. And this is a completely different effect because this is a stabilizing effect. So oxygen has two different effects on carbocations. Oxygen substituents have two completely different effects in electrophilic aromatic substitution. So one effect of oxygen substituents is that they destabilize carbocations because they're electronegative. But there's a second effect, this resonance donation effect, that stabilizes Arenium ions. So which one is more important? And that's super easy for me to tell you. It's the resonance stabilization that's more important. Resonance stabilization wins out over this destabilization by electronegative atoms. Overall, if I were a carbocation, I would rather have that electronegative oxygen there because it has lone pairs. I don't care how electronegative it is. Even if it's fluorine, the most electronegative atom in the periodic table, if I were a carbocation, I would love to have a fluorine atom there because fluorine has lone pairs that can donate in and satisfy the octet rule. That tells you a little bit about the importance of the octet rule. So So number 2 is the most important. Resonance donation wins out over electronegativity. So if you can have a lone pair next to you and you're a carbocation, go for it. That's the way to win and become stable. Okay, so let me summarize. I've got this huge summary now. I just spent a lot of time trying to explain to you, ortho, para, all these Arenium ions. And really all you need to do is memorize this one chart, I say. Well, you need to know how to draw out Arenium ions. But this one chart right here summarizes all of these effects. And I expect you to know this chart. Moreover, I expect you to know how to use this chart. That's the important thing. I would never ask you to draw this chart on, that's not the kind of questions I ask on the exam. So let's take a look at this, let's take a look at these effects here. So the first important point is what I've done is I've ranked different substituents. If you have one of these substituents on a benzene ring, and so let me go ahead and draw out a benzene ring here so we can clearly see what I'm talking about. If I have a benzene ring that has one of these groups on there, and maybe I'll symbolize it Y here, that can be any one of these groups. That's my mysterious symbol. So I've arranged them in terms of things that make electrophilic aromatic substitution super fast, and amino groups are the best at that. They activate benzene rings and make them react super quickly. And we call these groups towards the top here, we call these activators. And we refer to benzene rings that have these groups as activated. So amino groups with lone pairs, those activate benzene rings. Alkoxy groups with lone pairs, those activate benzene rings. Amido, you can't tell there's a carbonyl group here on this carbon. Amido groups, because the nitrogen still has a lone pair, are still activators. So all these things towards the top are more reactive. I guess I'm comparing everything here to just a regular benzene ring where if the substituent Y is an H, that's just benzene. So all these things above this dashed line react faster than benzene. Now, take a look at the substituents toward the bottom. If I have a halogen, if I have a carbonyl group like an ester, an amide, an aldehyde, a ketone, doesn't matter. As long as there's a carbonyl directly attached to my benzene ring, that's going to react more slowly than benzene. Sulfonic acids cause benzene rings to react more slowly. Ammonium groups, nitro groups are the worst. They really slow down benzene rings. So down here at the bottom, any one of these substituents I would refer to as a deactivator. And I would refer to one of those benzene rings that has one of these as deactivated. So let me spell out deactivators. And the strongest is the nitro group. Nitro groups really slow down electrophilic aromatic substitution. Now, there's this semi-convenient generalization that when you have these activators on your benzene ring, those tend to react most quickly at the ortho and para positions. These activators favor ortho-para substitution. Gee, that's convenient. Activators favor ortho and para substitution. And if I compare that down below with benzene rings that have deactivators, and let me give it a different symbol here, Z, for deactivator, just so I'm not using the same symbol. If I have a deactivator down here, all of these favor substitution at the meta positions because the ortho and para positions are slowed down so much. It's not that the meta positions are better, they're just not screwed over so badly. So if I have any one of these, like a nitro group, if I have a nitro group, it messes up ortho and para substitution so much that you only get substitution at the meta positions. Now, unfortunately, there's not a perfect match. I can't give you a simple rule that all activators are ortho-para. Well, maybe I could give you that rule. Let me just show you that there's a break in this generalization. When you look at the groups that are ortho and para, that favor ortho and para substitution, it's everything above this line right here. In other words, halogens. I'll just write ortho, para. Even halogens, which are deactivators, which slow down electrophilic aromatic substitution, they're kind of the fly in the ointment. So they are deactivators, but they still favor ortho and para substitution. Anything below halogens in our ranking here These favor meta-substitution. So you can see there's not this perfect match between activators and deactivators in ortho and para. Halogens are this outlier. Halogens, even though they slow down electrophilic aromatic substitution, are still ortho-para directing groups. They cause this next substituent you add to the ortho and para position. So that's going to cause you some consternation. It's going to take something that would otherwise be simple to memorize and turn it into something that is somehow not easy to memorize. And it always gave me pause when I was trying to use that kind of information. Okay, how do you use this? How do you use this kind of a sheet here? I'm going to give you yet one more exception for the Friedel-Crafts reaction. Right? You know 5 reactions now, 5 recipes for adding substituents. And I told you that Friedel-Crafts reactions will have exceptions, and it's mainly the exceptions that make this whole chapter hard. You guys are good enough to memorize 5 reactions. I'm positive of that. But it's all these exceptions we're going to throw in, and this ortho-para business that makes it hard. Okay, so here's this exception for the Friedel-Crafts reaction. Yeah. Did I? Oh, is this the slide that I skipped? Ah, yes. Thank you for cluing me in on that. Okay, so before we get to that exception, sorry, I jumped the gun there. I want to show you how not to use those rules from the generalizations we had from the previous slide. One take-home lesson that you might get from that previous slide was some sort of a rule like, oh, nitro groups, those are meta-directors. Those are deactivators. That's what that previous Uber slide showed you. But I want you to be super careful about how you use that. What does that mean if I say that a nitro group is a meta-director? So here's what you might be inclined to say. You might be inclined to say, oh, yeah, we covered this in class. Nitro groups are meta-directors. That means that nitro groups always add to the meta position. No, that's not what it means. When I say a nitro group is a meta-director, what I mean is if there's a nitro group already on the benzene ring, the next substituents add meta. Right? The way to analyze this problem, this would be the incorrect analysis. It's not that you can't nitrate this ring. The way to analyze this is to say, oh, there's a chlorine group on that benzene ring. And if there's a chlorine group on that benzene ring, chlorine groups are ortho-para directors. That's the way to use those general rules. And if chlorine group is an ortho-para director, what that means is I'm going to get about a 50-50 mixture of ortho substitution, and I don't have to draw the other ortho substituted product because it's identical. So out of this, you'll get about a 50-50 mixture, about 1-to-1, just always assume it's 1-to-1, of both ortho and para substituted products. That's the way to use those rules. In other words, it doesn't matter that nitro is a meta-director. You look at the substituent that's already there on the benzene ring. If you wanted to synthesize this meta-chloro-nitro-benzene product here, the way to synthesize that is to start with the nitro group on the benzene ring first. If you wanted to synthesize this compound over here, you need to nitrate the benzene ring first. And then, now you can use this rule that nitro groups are meta-directors. Now the next substituent you add, no matter what it is, the next substituent will end up meta to the nitro group. So if now we use our chlorination recipe, chlorine, FeCl3, and that's how you make that product. So you need to learn these rules, which groups are ortho-para directors, which groups are meta-directors. And if you can't remember those rules, you're going to be stuck, because I promise you every single instructor on their exams is going to put questions like this where you have to strategize which group do I put first and which one is the ortho-para director. That's exactly the kind of question that you're going to end up seeing on a standardized exam. So I've got one last thing to show you before we leave, and it's actually not that complex to show you, but kind of essential here, because this will help you to get geared up for, and it's an exception for the Friedel-Crafts reaction. and that is that you cannot do Friedel-Crafts reactions on benzene rings that are too deactivated. And how deactivated should it be? It's this deactivated. Anything below this line is too deactivated for you to do Friedel-Crafts. So in other words, if I take nitrobenzene, right, that's the most deactivated of all, and I use my recipe for a Friedel-Crafts reaction, that nitrobenzene is just going to laugh. It's going to be like, you got to be kidding me. Take your shit and get out of here, because you're not going to react with that. You can only do Friedel-Crafts reactions with things that are above this line. So the rule here is anything that has a meta-director, you cannot do Friedel-Crafts alkylations, you cannot do Friedel-Crafts acylations. It's just not reactive enough. If you want to make this compound, you can synthesize this compound here, but the way you would have to synthesize is you would have to be very clever and strategize. You have to start with the other group on the benzene ring. Start with that acetyl group already there, the carbonyl group already there, and then put on the nitro group. That carbonyl group is already a meta-director, and so if you use your nitration recipe, that's what would give you the product. So let me just put a big X here. You're not going to be doing any Friedel-Crafts on nitrobenzene. Ultimately, what you're going to find is that anything that has a meta-director, you don't do Friedel-Crafts on those. Too slow. But what we'll see later, I don't know if we'll see it later. We'll just see it right now. Things that have amino groups on them are too activated. And you can't do Friedel-Crafts on those either. So do not do Friedel-Crafts, and I'm not going to explain to you the problem with having amino groups on benzene rings. But there's only this narrow window of reactivity where you can do Friedel-Crafts reactions, acylations, alkylations, and you need to know that window. Super important that you don't try to do Friedel-Crafts on rings that are too activated or too deactivated. Okay, so we'll come back on Friday, and we're going to finish all of this stuff up. We have covered most of the major stuff for this chapter. We just have to learn how to fiddle around. Okay, so remember there's a review session tonight, the Department of Peer Tutors, at 5 to 7 p.m. Go to that.